This is the introduction to kinetics. This is later in the 50s. I got involved in the kinetic studies using my long forgotten math background. Some of you may or may not know what this is. So this is actually used for us to get kinetics data. We're not actually going to use a lot of calculus, in fact, very little calculus at all. I'm just going to show you where calculus applies. So if you're not in calculus, you've never had calculus, don't worry, but I'm going to show you where it does apply. Okay, next we have our learning goals. So the learning goals, kinetics is going to be split into two parts. The first one is just going to be, do you understand the factors that affect the rate of reaction? And this is pretty easy. This is mostly conceptual. Okay, so do you understand that the state of matter determines how fast a reaction goes? Do you understand that the concentration, those kind of things? The last one is going to be more mathematical. Okay, and when we look at the math, it's going to be things like, do you understand the relationship between time, concentration, and rate of reaction? Okay, and that's going to be a little bit more difficult. So we're going to take a look at what are called zero, first, and second order reactions. And then in the second part of this, we'll extend our knowledge and go and start to look at things that are a little bit more complicated than that. But for now, kinetics. Kinetics is basically the study of how quickly a reaction will occur. We already know from pre-AP chemistry and what we've talked about so far that reactions happen. They do happen. The speed of the reaction determines a big deal. Okay, so for example, the what we'd like to talk about is the idea of a chocolate chip cookie. If you had a chocolate chip cookie and you had an equivalent mass of TNT, okay, trinitrotoluene if you want to know the exact name. It turns out that this chocolate chip cookie has more energy in it than the equivalent weight of TNT. The reason why the TNT results in this is the reaction that TNT goes through is a very, very fast reaction. In other words, it releases all of its energy at once, as opposed to when you eat the chocolate chip cookie, all of the energy that is released from the cookie into your body happens in a slow, stepwise process. So, kinetics is the study of how quickly these reactions actually occur. Now, the first thing that can affect the speed of a reaction is the state of the matter in which the objects are reacting. So, for example, a solid is pretty non-reactive, and the reason for that is multifold. If I have a reactant right here and my solid right here, only a couple of molecules can interact at this point. So even if you directly touch solids together, that's the only molecule that is going to be able to react with this other substance. So solids are not very reactive. Now, on the other hand, aqueous liquids and gases are very reactive, and it's because they have mobility. So these molecules can move and rearrange themselves, and they can get in between the crevices that you just can't with a solid. So because of that, we have aqueous liquids and gases that are going to be extremely reactive as compared to solids. Next, you have the idea of mixtures. A homogeneous mixture is going to react much more quickly than a heterogeneous mixture. And the reason is the same thing, the closer physical proximity of the reactants. So remember, with a solid, the solid was pretty non-reactive because all the molecules that weren't on the surface that was reacting, these molecules right here wouldn't react at all. You have the same thing whenever you form a heterogeneous mixture. If you look, you're forming a layer, and that layer presents only one place in which these molecules can interact. Okay, whenever you have a homogeneous mixture and everything's mixed together, you can have reactions occurring everywhere in the container. So a heterogeneous mixture is not going to be nearly as quick in reacting as a homogeneous mixture. Next, you have concentration. Concentration can also affect the speed of a reaction because you have to think about concentration as being the density of particles. Let's say that for a reaction to occur, you need two of these particles that are on this image. Okay, if you look over here, the likelihood that these particles are going to interact, any two of them, is relatively small because in order for these two things to react, they actually have to come into physical proximity with one another. If you compare that to an equal sized area over here, the reaction is much more likely to occur because you have molecules or atoms that are in the same physical place. So the concentration, which is the density or how many reactants are in a given volume, the higher the concentration, generally speaking, the faster a reaction will occur. Next, you have temperature. Temperature is also generally speaking, the higher the temperature, the faster the reaction is going to occur. And the primary reason for that was whenever you increase the temperature, what you're doing is you're increasing the speed of individual molecules. Well, if molecules are moving more quickly, they're more likely to encounter another molecule. Okay, if they're moving relatively slowly, they may pass each other and not be able to react. So the speed of a molecule is directly influenced by the temperature. In addition to that, there's an energy barrier that we're going to learn about a little bit more about later. For every reaction, you actually have to overcome this energy barrier. You may have seen this in biology, but you have to overcome this barrier. Now, in biology, they talk about the idea that enzymes actually lower this energy barrier, and they do. We're going to talk a little bit more about catalysts in a little bit. So you can lower that energy barrier, but also if you raise the temperature, you're starting the reactants at a higher level on that energy barrier. So because of that, they don't have as high to go as they originally did. So by increasing the temperature, you're increasing the initial energy, so you don't have to jump as much in order for the reaction to occur. You're also making the molecules move faster, so they have more collisions, which make it more likely that you are going to have a reaction occur. Okay, next we have a catalyst, and a catalyst is actually something that will bond with one or more reactants. Usually it bonds with two reactants, and then it moves them physically closer to one another. So if you look at these two dots, I guess we should change the color here. If you have these two dots that are trying to react, but they're all over the place, it's hard for them to become in physical proximity to one another. If you have one that bonds with the catalyst and another one that bonds with the catalyst, now they're right next to each other. So now they can be attached to one another, and that right there is what you have for a catalyst. Now, in biology, you talk about enzymes as catalysts. We're generally not concerned with enzymes in chemistry. Instead, we tend to have things like platinum or gold or even to lesser extent silver act as catalyst. Now, the reason why these tend to be used as catalysts is because they do not react with the substance that's there. Okay, if you have platinum and you have oxygen, okay, platinum won't rust, and because platinum won't rust, the oxygen can attach to the platinum and then react with whatever's there, like lithium or something, and those can go together. So the catalyst has to be something that does not react, and when these things bond, is still originally there. It does speed the reaction because it lowers the activation energy. It's making these two things closer to one another so they'll bond as soon as they get in close proximity to one another. An inhibitor is the exact opposite of a catalyst. It doesn't really slow it down, instead, it stops the reaction. So, generally, if you think of an inhibitor as like an enzyme, what it does is it blocks that enzyme so that whatever's coming in cannot attach to it anymore. So, what an inhibitor will do is it will stop a reaction from occurring. Because it binds to one or more of the reactants. So if you have a whole bunch of silvers, okay, and then you have a whole bunch of nitrates, and you put in something that attaches to the nitrate, well, now the silver and the nitrate can't react to one another. And so that's what an inhibitor is. Okay, we tend to not work with exclusive inhibitors, so what you'll be told is you'll be said, this substance is an inhibitor. You don't have to memorize anything as far as inhibitors are concerned. Okay, so now we're looking at the rate of reaction. The first question we always have to ask ourselves is how can we measure it? So whenever you measure the rate of reaction, there's a couple of things that you can look at. So number one, there's a reaction that you have that if you had a solid piece of metal and a reaction was occurring, some of this solid metal may be disappearing. So you can look for a change in mass. That's one way to do it. Another way to do it is you can look for some sort of absorbance, like we've talked about with Beer's law. Okay, or if there's another way to find some sort of change in concentration. Now, if you're doing absorbance, you're doing concentration as well, but you're looking for some sort of change in the number of moles or in the number of mass of the particles. Now, the good thing about whenever you're measuring a rate of reaction is you only have to measure one thing in the reaction. So, for example, if I have the reaction of A to B, I don't have to measure A and B in order to figure these values out. Because I know what the chemical equation is, I can measure one of them and then figure out what the other one is going to be. And that's not just for a one-to-one reaction, but it would also work for like A plus B or A plus 2B goes to C. If I know how much A disappears, then I know how much 2B would disappear, and then I know how much C would appear. So you see an example of that here. We start with 1 mole of A, 0 moles of B, and then after a certain amount of time, you see how the number of moles change. Okay, so you can use the balanced chemical equation, and you can go from there. So next, we see an example. You see reaction concentrations. This right here is what we call chlorobutane. Okay, it's called butane because it has 4 carbons, and we have methyl, which is 1 carbon. We have ethyl, which is 2 carbons. We have propyl, which is 3 carbons, and we have butyl, which is 4 carbons. Everything after that follows the rules of penta, hexa, and all those rules for shapes that you have. These are the 4 ones that are kind of strange. So this is called chloro because it has 1 chlorine, and then butane. Okay, so now you react it with water and you get this. This is called butanol, and then you have hydrochloric acid as well. So this is the reaction that we actually have occur. And it says butanol and hydrochloric acid must increase. And the reason why they know they must increase is because this value is going down. Whenever the concentration of the chlorobutane decreases, it's indicating that the reaction is occurring. Whenever we know the reaction is occurring, then we can say that the products are being made on the other side. So you can actually look at specific values. So for example, I can look at the concentration at 50 seconds. And I can say at 50 seconds, the difference between these two values right here and the difference between these two values right here represent a change in time and a change in molarity. Well, you can look at the rate that a reaction is actually occurring by the change in molarity. So what I have here is I have this right here is the change in molarity of the chlorobutane. So in other words, that's how much decreases, how much disappears. And really it should be this minus that, because this is going to be a negative value because it's how much disappears. Okay, 0.0095 hydrochloric acid has to up here because it's on the other side, and this is a 1 to 1 to 1 to 1 reaction. So however much hydrochloric acid disappears, I have to have the same amount of hydrochloric acid up here. So it says right here, let's go through an example problem. It says, what is the physical state of the reactant? Whenever you look at this, this is starting to be kinetics data. Realize that in addition to the change in concentration that we talked about, gases don't have concentrations. Instead, they have pressures. So talking about the pressure of a gas is the same thing as talking about the concentration of an aqueous substance. So when I want to know what the state of the product is, I look here and I see that it's in atmospheres. I know that the product must be a gas. Now I also know it has to be a product because I'm starting out at a small value and I'm making more of it. So since I'm making more of it, it's going this way, which means the product has to be a gas. Okay, it says, what is the average rate of formation for the first 9 seconds? So now if you were to look at this, you can't actually answer this question directly using the data table. Because if you look, you have data from 0 to 50 seconds. So instead, you have to you can look at it from this perspective. You can say, if I want to know from 0 to 9 seconds, I have to look within this framework right here. And so we did this already. We said that the change in concentration is negative 0.0095, and then that occurs in 50 seconds. Now, the rate between these 2 points we are assuming is the same because those are the 2 data points that we have. Now, that's not a safe assumption because if you look, you can clearly see it change as you go through. It's not a consistent pattern as you go through. So this is not a good set of data. So instead, what if we said the first 9 trials? And we said all the way through here. Okay, if we're going to do the first 9 trials, then we can look at it and say, okay, the change in concentration is going to be, for A, is going to be negative 0.9800 divided by our 800 seconds. Now this represents the change in concentration, and remember that's the change in concentration of A, just like this was the change in concentration of A. Now if you're looking at this, it says what is the concentration of D? So remember, I'm going to change colors here just so it's a little bit easier. Whenever you have A go down, you have to have an equal amount of D go up. but because of the stoichiometry, it's a 1 to 3 relationship. So whatever your disappearing concentration is here, you would have to multiply it by 3, and that would equal your concentration of D. Okay, so let's say, for example, let's just say that this is 0.001. It's pretty close to that. So 0.001 molarity per second. That would mean that the concentration of D would have to be a positive 0.003 molarity per second is the formation of D, because I have a 3 to 1 ratio. Okay, next it says 20 grams of copper will react with excess silver nitrate in solution. So the first thing I want to do is write a chemical reaction. I say copper solid plus AgNO3 in solution lets me know that it's aqueous. I know this is a single replacement reaction, so I'm going to have copper nitrate plus silver. Now the question says is what is the rate of formation of silver? So in other words, I'm looking for how much of this is made. So there's a couple of different ways you can answer this because it doesn't give me a unit. I can actually answer it in grams per second, or I can answer it in molarity per second. Either one will work depending on what the question is actually asking for. So it says 20 grams of copper is reacted. So I have 20 grams of copper, but afterwards there's 18.8 grams. So really what I'm using in this reaction is I'm using 1.2 grams of copper in 10 seconds. Now I know it's in 10 seconds because it says you introduce an inhibitor that halts the reaction at that point. So everything that reacts in this initial 10 seconds, and this is 1.2 grams of copper. So now what I can do is I can go from grams of copper to moles of copper. So now that I'm in moles of copper, I can use the stoichiometry of this equation. Now this is a 1 to 1 to 1 relationship, so I can say 1 mole of copper is equal to 1 mole of silver. Now, if you were originally answering in molarity per second, you're actually there. Moles of copper, grams of copper, grams of copper. What you're left with is seconds and moles of silver, which is what I wanted to do. If you were answering in grams per second, you'd have to add one last step, and that one last step would be 1 mole of silver, and then I think it's like 107.8 or 108.7 grams of silver. So it just depends on what the question is asking for, but basically you're using the same stoichiometry and one measured value to predict the other value. Okay, so now there are different rates of reaction. Not everything occurs at the same mathematical function. In fact, there are some reactions that do not depend on the material present. So they do not depend on the concentration. It's the same if they have one molecule or if they have 7 billion molecules. Okay, whenever we have those, they're called zero order reactions. Zero order. Now, the reason why they're called zero order is because the concentration does not affect the reaction at all. A couple of things are things like nuclear half-life. A nuclear half-life is if you take something like uranium-235, it will spontaneously turn into barium and krypton, and it will occur like this regardless of how much uranium-235 is there. In fact, it occurs at the same rate always, and we can actually use this to measure the age of the Earth. So because of that, this equation does not depend on time. So with that being said, it doesn't depend on how much stuff is there, just how long the reaction is gone. So we create this graph of the rate of reaction versus the concentration. And no matter what you do to the concentration, the rate of reaction remains constant. That's why it's called a zero order reaction. There is no slope to this. Now, this is pretty rare with chemical reactions. Whenever this occurs with chemical reactions, they tend to be unimolecular, which means there's only one molecule that's performing a change on its own. This is pretty rare, but it does occur, and it's the easiest one to start off with. So like I said, we call these zeroth order reactions, and they're reactions that do not change rate. So if you were to look right here, this is my concentration of A. It starts at 1, goes to 0.95, goes to 0.90. The rate is negative 0.05 molarity per second every time. Just so you know, whenever you have molarity per second, sometimes that's written as ms to the negative 1. because remember that the negative 1 means divided by. Or sometimes it's written as moles per liter second. They're all the same thing, but they refer to this rate. Now, the decrease in A is the same throughout, so we say that the rate of the reaction is unchanged. Okay. So one of the things that we really want to do is we want to spend some time on these graphs, because these graphs tend to be what you see on multiple choice questions and even on free response questions. So we talked about the idea of rate versus time, and that you're going to get a constant slope, or no slope, zero slope. So this is a zero order. Also, if you take a zero order and the concentration and the time, so these are two different graphs. You have a concentration versus time, and you have a rate versus time. Using these two graphs right here, you can actually get an interesting relationship. So for those of you who are in calculus, you can actually take the derivative of this graph. If you don't know what a derivative is, don't worry about it. And the derivative of this graph would give you this graph. So the two graphs are related. Or you can take the integral of this graph and get the original graph. If you don't know what I'm talking about, don't worry about it. You don't need to know any calculus for this class. So, zero order reactions continued. If you take that graph, that constant graph that we had that said concentration and time, you can actually take this graph and you can come up with an equation for it. Now, the goal of most of these kinetics problems, is to look at a linear equation for the graph. See how I have a straight line and I have a negative slope. What I can say is that the concentration of whatever I'm given is equal to this right here, the slope. The slope in this particular case is called k. It's a lowercase k. And it's going to be negative because you always have a negative slope as the concentration goes down. Times the time plus the initial concentration. Now, if you don't know where that came from, it came from applying y equals mx plus b to this graph. Y is going to be your c value. M is the slope, which we're calling k now. X is t, and then the plus b is your original value. It's the concentration that you had to start off with. It's your y-intercept. So, one of the things that you'll see for a zero order reaction is you will see it in this form right here. You will also see it as written as rate is equal to k a to the 0. This is a lowercase k. So that's where it comes from, the zero order reaction, because it doesn't depend on a at all. It's got a zeroth order exponent. And then the last thing you need to know is that these units of k are going to be molarity s to the minus 1. And the reason for that is the rate value is always going to be in molarity per second, or molarity s minus 1. That's what the rate always has to be. So the units of k will change to match so that it always ends up being molarity s to the minus 1. And that'll make a little bit more sense after we go through the next set of data. Okay, next you have changing reaction rates. Okay, with changing reaction rates, you see that this is no longer a zero order reaction. Instead, what you do is you see a change each time as you go through. So there's no longer a consistent pattern as you go from one to the other. So the average continually changes as you go through. If you look at the first data point and this one, that's the average, and this is the average, and this is the average, and the average changes. So whenever you have this change in the reaction rate as the reaction proceeds, we know that it is no longer a zero order reaction. A zero order reaction would have a constant average change. So the fact that the lower reaction rate, as you change the concentration, the rate gets slower, tells me that this reaction is going to depend on the amount of chlorobutane that I have. So when you have a changing reaction rate, the first one we're going to look at is called a first order reaction rate. And you see an example right here with a first order reaction rate. The fact that the rate continually changes as the concentration goes up is very different from what we had previously. Before, we had the rate and the concentration, and it was a flat line across saying that it didn't make a difference. So we see now that this is an example of what we call a first order reaction. So do you see how the average rate changes as we go from point to point? So because we have a continually changing rate, a lot of times people will choose to study with this with calculus. Now we're not going to study it with calculus, so don't worry about it, but the idea of a changing rate is present in calculus. So, if you were to look at the graph of concentration versus time, you would see that there would be this curve downward. The fact that the concentration is going to affect the rate, which means as the concentration goes down, so does the rate change as well. So if you look at the rate would be the slope here, and the slope here, and the slope here, and the slope here. The rate is continually changing as our concentration decreases. So you don't see as drastic a changes between T0 and T50 and T500 and T800. So if you look at these, it looks like they're drastically different, but you have a 300-second gap here and a 50-second gap here. So you have to be real careful when you're looking at experimental data to make sure that all the points that you're looking at are very similar. So whenever you have a first order reaction, it's really hard to determine what the overall rate is because the graph is curved. So we're not going to use this particular curve. Instead, what we want to do is we want to linearize the graph somehow. In other words, we want to turn this graph into the point where it's a straight line graph. Now, one of the ways that you can actually figure this out for a first order reaction is if you knew calculus, and once again, we're not going to deal with calculus, but you could do something called an integral. We're not going to do an integral here, but what you can say is, what can I graph, or what can I do to the concentration so that I end up getting a straight line? A straight line this way, or a straight line this way, because I can deal with a straight line. Now it turns out that for a first order reaction, you can actually use something called the natural log. Whenever you take the natural log of the concentration, you now have a linear graph. So you have time, you have the natural log of the function, and then once again you have the slope, which is going to be our minus k value. So just like we had before, now that we have a line, we can use our general equation of the line, y equals mx plus b. And we can take this and we can figure out what an equation for a first order reaction is going to be. So in this case, our y value is going to be the natural log of a. And then our m is going to be the slope, which is going to be our minus k value. Now the reason why it's minus k is because the slope is downward again. And then your x value is going to be your t, and then your y-intercept in this case is going to be the natural log of your initial concentration. So you see that here. A first order reaction is going to say rate is equal to k a to the first. This is why it's called a first order reaction, is because the rate is dependent on the concentration of A to the first power. So if I were to double the concentration of A, I would expect a doubling in the rate of this reaction. If it were to be tripled, I would expect a tripling of the rate. If it were to be cut by a factor of 3, I would expect the rate to be reduced by a factor of 3. So because of that, you have the linear version of the linear version of this equation, which is natural log of a equals minus kt plus ln a0. And a lot of people get confused. They say, okay, I've got two equations for a first order reaction. Which one am I trying to use, or what am I trying to find out? And in order to do that, you have to say, okay, well, am I interested in the rate? Because if I'm interested in the rate, I would use the top one. Am I interested in some sort of function of time? Is time anywhere in there? Because if time is there, then I'm going to use the bottom equation. Now, just like we said before, the rate has to be in units of molarity per second. So you have to manipulate the units of K such that you end up with molarity per second. Now remember, A is going to be a measurement of concentration. So now I've got molarity there. The only thing that I have to put in for the parentheses for the units of K in a first order reaction is seconds to the minus 1, which is going to make the units match up. So you can see this is very different from a first or from a 0th order reaction. So if I were to compare this to a 0th order reaction just real quickly, I'm going to change it to a different color. For a first order or for a 0th order reaction, we had rate is equal to Ka to the 0, which now we have rate equals Ka to the first. So when the 0th order reaction, there is no dependence on A at all. A doesn't affect the rate is a constant regardless. For the 0th order reaction, we had the concentration of A is equal to minus Kt plus the initial concentration of A.
Now, if you look, that's very similar in structure between the first order and the zeroth order. The only difference being whether it's the natural log or the actual concentration. And then the units in this case were going to be molarity per second. For K, which now the units of K are going to be in seconds to the minus 1. Okay, so there is also a second order reaction. We are going to be responsible for AP, the zeroth, the first, and the second order reaction. So this is the last one we need to look at. And whenever we have an example of a second order reaction, they generally come whenever there is a dependence that there's two molecules that are the same thing that are reacting. So whenever you look at this, you would say that the rate of the reaction increases on an exponential scale as you increase the concentration. So as I'm increasing the concentration, it's not just going up at a straight line like I would predict with a linear, but instead it's increasing in an exponential fashion. So reaction rates. If you were to look at the concentration in time as the reaction occurs, you're going to once again see a curve like we saw in first order, which is going to make it difficult for us to interact with. So the first thing you do is whenever you see a curve for a concentration versus time graph, you're going to say it's first or second automatically. Now you have to do some calculations in order to figure out if it's going to be first or second. You can't say because of the steepness of the curve it's first, because of the steepness of the curve it's second. You can't do that. You're going to have to do some math in order to figure out what it is. So once again, we have the idea that this rate is hard to determine from a curved graph. Like I said, you could do some calculus if you knew calculus, but we don't know calculus, so we're going to try and make this a straight line graph. So in other words, how are we going to be able to take this and turn it into a straight line graph being a positive or negative graph? Because then I can use my y equals mx plus b. So the whole idea is we're trying to linearize it, make it into a straight line so that we can do some math with it. Okay, so it turns out that for a second order reaction rate, you have to look at the inverse of the concentration. What the inverse of the concentration is, instead of saying A, we say 1 over the concentration of A. Now, as a result of this, what we get is we get a flip in the graph. Instead of having a negative graph and a negative graph like we have for zero and first order, for second order you get a positive graph. And that's one of the hallmarks of a second order that makes it really easy to find is the fact that it actually has a positive slope. Okay, so now once we have this positive graph, okay, this is actually the negative graph. This is our first order reaction. Okay, once we have our positive graph, we can say 1 over A and we have time. Well, if I'm going to look at this line, I'm going to have 1 over A, which is my y. I'm going to have minus k, or this should be, excuse me, positive kt. It's going to be positive kt because the slope is positive. And then you're going to have 1 over the initial concentration, which is 1 over our initial concentration there. So you're going to see very, very similar structure. This is very similar between the first and the second order, just what is here and what is here. Okay, that's going to make all the difference in the world. And the unit is going to be molarity to the minus 1, s to the minus 1. And here's why. The rate is going to be measured in molarity per second. I have molarity for the concentration, which is then squared. So I need to find a way to get rid of one of those molarities by putting molarity on the bottom. And then I need seconds on the bottom. So I put molarity to the minus 1, seconds to the minus 1. And when I do that, that allows this squared term to cancel out with this molarity. And now I'm in molarity per second, which is what I need to be in. Okay, so we're going to spend a lot of time with these with some examples in class, but for now, just to show you as an example, what is the rate law based on the graphs below? So if you were to look at these, we have concentration versus time. So this right here and this right here, I've got concentration versus time. I know that if I had a straight line here, it would be a zeroth order reaction. I do not have a straight line, so because of that, I know that it is not zeroth order. So the next, I look at the natural log, and I look at the natural log and time, and if I had a straight line, then it would be a first order reaction, but I do not have a straight line, so then I look at the next one. It's 1 over A and time, and I have a straight line, so because I have a straight line, I know this is going to be a second order reaction. In other words, this reaction is going to be something like A plus A goes to B. And then next I have sketched the graph and labeled the units of K based on the rate law. So I look here and I say that this right here is a second order reaction. And now I need to decide what kind of graph am I looking for. There's actually two graphs. Okay, the first one would be something along the lines of rate and concentration of A. And if you had that, the rate would decrease as our concentration of A decreased as well. So you're going to get a graph that looks, oh, excuse me, I'm sorry. It's going to, as the concentration increases, the rate is going to increase as well. Okay, so you could also have something like the concentration of A over time. And when you do that, you're going to get a curve that goes downward. But none of those graphs are particularly useful to us because they don't have a straight line. So instead, what I'm interested in is the 1 over the concentration and time. When I do that, I'm going to get a straight line that goes downward. Excuse me, I'm having a tough time with this one today. It's a straight line that goes upward, and then the units of k represent the slope. So the value of the slope is going to be k. We're going to spend a lot of time with these kinetics problems in class, but you should have a pretty good understanding of what's going on with kinetics.